Hello. In the previous video, we were discussing about the magnetic susceptibility, and we had obtained certain relations related to the magnetic material with respect to the magnetizing field that it is exposed to. And I had also mentioned that we'll be discussing about the various types of magnetic materials such as the dia, para, and ferromagnets. But before that, let us just discuss about the magnet. Where does this magnetic property comes from? What is the idea behind the modern view behind this kind of a magnetic property? The explanation for this kind of a magnetic property. Well, in the previous video, I had also uh, mentioned that if we have a solenoid, or so as to say even a single loop which is carrying some amount of current in it, then this current that is flowing across that loop, this is a circular loop of a certain radius, and this current that is flowing across that loop, and there is a certain area of that loop. So this is the area of that face of that loop. So this is A, and the current is I. So as I had mentioned, that this loop would be behaving like a magnetic dipole. There will, if we have a solenoidal arrangement, then there will be number of turns, but for simplicity I have considered a single loop over here, and the magnetic dipole moment in that case m, that is equal to I multiplied with A, where A is the area of that loop. And let's just be contented with the magnitude as of now. Well, there is a complete derivation of this thing, that we have the magnetic field intensity. We can determine the magnetic field intensity at a given point along the axis. So let that point be P, and it is lying along the axis where the radius supposedly in this case is A. So let me give it to you in another ink. So let us say that the radius in this case is A. So this is the radius A, and then we obtain the and from the edge of the uh, circular coil, the point P is lying at a distance of say R, and from the center it is lying at a distance X. So with all these parameters available to us, what we obtain is that we obtain a magnetic field intensity at that point P. As of now, we are just discussing the magnitude of it. We'll be going over to the direction pretty soon. Now, in this case, if we are to write the expression for it, so it is simply mu 0 divided by 4 pi, that is the constant which is associated with magnetism, and mu 0 by 4 pi, and the dipole moment in this case is m, but the expression in terms of the current that we have is simply I and a squared, where a is obviously the radius as I mentioned, and divided by the cube of this distance, that is r. So it is simply r cube. But if I write it explicitly as mu 0 by 4 pi, I remains as such, and instead of well, there is a square, but instead of r, what I write over here is simply the form of r, that is x squared plus a squared under root will be r, and cube of that will be simply 3 by 2, x square plus a square to the power 3 by 2. So this is the expression. In fact, this is not 4, this is actually 2. This expression can be obtained. It has been derived in the portion of magnetic effect of electric current or moving charges and magnetism that you can refer to in the playlist. Now, if I compare it to a magnetic dipole, so this is a bar magnet, which is obviously a magnetic dipole, and it has the north pole, it has the south pole. uh, quite okay with that. And from the center of the dipole is of length 2L, that is the distance between the poles, and from that center of the pole we are to determine the magnetic field intensity at a point along the axial line. And as I mentioned in the previous video, about previous or prior to that, this is quite similar to that obtained in case of an electric dipole, and the expression that we obtain over here for the field intensity is simply, again, we are concerned with the magnitude for now, and the expression that we get over here is B is equal to mu naught, and there was 2p in case of the electric dipole, for the dipole moment being p. Here we have mu naught by 4 pi 2m, where m is the magnetic dipole moment, and 2m divided by the distance over here is x, so distance over here is x cube. So this is the uh, expression. In case of electric field, it was the electric field intensity K2P divided by x cube. Here we have K stands for mu naught by 4 pi K2M divided by x cube. That is the expression for the magnetic field intensity at a point along the axis of the magnetic dipole. Now, this is similar to this magnetic dipole, and if that is the case, when a current, well, that was obtained by Oersted experiment. The whole lot has been discussed in the portion having in the portion of magnetic effect of electric current, how the electric current leads or moving charges in magnetism, that is, where as a charge moves, how the magnetic field is associated with it. Moving charges means the current that is flowing across a given medium or across a given conductor, which is the case. We have drawn the current in a given loop over here. So if we have the same case where this is behaving like a magnetic dipole, this is a magnetic dipole, natural magnet, bar magnet. So therefore these two terms along the axis of the given bar magnet and along the axis of the coil, magnetic the current carrying coil, they must have the same thing. Now there's one more mistake over here. There won't be any pi. The expression is simply 2 times of that's not 20, that's 2 times of the thing at the denominator, that is 2 times of x squared plus a squared whole to the power 3 by 2. Now if we are to compare these two, let us just do that. So now I write the expression, this expression, mu naught, the top one, the mu naught I a squared divided by 2, there was no pi over here, so 2, and let me just cancel it in case you may consider it as 20, as you will be skipping through the videos. So x squared plus a squared whole to the power 3 by 2. Now what I do is I just multiply a pi over here, the a square remains as such, and a pi over here, so 2 pi. Now the pi comes into picture, and this is a squared plus x squared plus a squared whole to the power 3 by 2, and this is equal to, well, if you observe this one, this is nothing but the area, so mu naught I times of a, where a is the area of this loop, this area that is a over here. Remember, small a is for the radius, and I have written the capital A, the bigger A, for area. Now 2 pi remains over here, and then I have some distance, that is r cubed. Now what if I multiply a 2 over here and a 2 over here? So what we have, this is not mu naught squared, I just multiply a 2 over here, so mu naught times of 2 times of IA divided by 4 pi, and this is r cube. Well, In this case, it was the cube of the distance x. In this case, it is the cube of the distance r. Well, in case this loop that you see over here, in case it is very, very small, the distances r and x will be nearly similar, isn't it? In case of smaller loops, x will be nearly equal to r, and in that case, so there won't be any comparison over here. So this is x cube, this is r cube, is almost the same. Mu naught by 4 pi, mu naught by 4 pi is the same, and 2 and 2, that is the same. So obviously these two terms, that is m, has to be equal to I times of A. Well, in case of direction, if you wish to know, then the direction in this case would be towards the magnetic dipole, because there's the south pole over there, which to which the field is getting into the south pole every time. And in this case, if we are viewing from this side, if you are the observer who is viewing from this side, then the current appears counterclockwise, and counterclockwise means this is the north pole, and so the field will be along this side. Well, uh, I just made the current to flow in the counterclockwise sense from that side. If you are observing from this side, it will be clockwise, and so clockwise means it is the south pole, and counterclockwise from this side, counterclockwise will be the north pole. So the directions are determined as per the direction of flow of current, and that is how you compare the magnetic dipole moment of a magnet, or so as to say, the magnetic dipole moment in case of a current carrying conductor. Now, with this comparison done and dusted, we do have a modern view on magnetism. The modern view on magnetism, or about the magnetism that is acquired by a magnetic material, well, that is attributed to the motion of the electrons in the atom. Now, modern view, magnetism. Well, we had studied that the magnetic materials, they have the magnetism as an intrinsic property within them. But how does this come? Now, we said that it is natural, it is naturally occurring, but the modern view says that it is natural because of the motion of the electrons within the atoms. Now, here is the axis of an atom, where the nucleus is right at the center over there, and the electron revolves around the nucleus. Now, electron is a charged particle, so it is a moving charge now, and there's bound to be some magnetism associated with it. Also, the case where the electron, if you consider the electron itself, now this will be the magnified view of an electron. So this is an electron supposedly, and with that magnified view, what we are trying to say is it will be spinning about its own axis. So it will be spinning like this about its own axis. So as it spins about its axis, it also contributes to the magnetism as well, because it is a moving charge and now it is spinning on its own. That is why it is definitely going to contribute to the magnetism. Now, what about this is the orbital motion and this is the spin motion. So the orbital and the spin motion of the electron contributes to magnetism. Well, because just now in this video as well, and in the videos concerning the moving charges and magnetism portion, I have discussed that this magnetic dipole, the presence of this magnetic dipole moment also suggests that definitely it is going to show the magnetic properties or the magnetic characteristics. But what about those materials? Now, the electrons obviously spin in every atom, and the electrons also move around the nucleus in every possible atom. So where is the magnetic property in the non-magnetic materials? Well, those things which are unmagnetized, for the case of unmagnetized materials, the alignment of the motion of the electrons is such that the fields, the magnetic fields, they are vectors, remember. So the magnetic fields, they mutually cancel out each other. And because of this cancellation of the fields, the net field that is associated with that kind of unmagnetized material, that becomes equal to zero. And that is how the explanation goes, the modern explanation for the magnetic property of a given material. And when it is exposed, as it is exposed to an external field, on being exposed to an external field, the magnetic, the atoms and the electrons, they are somewhat aligned in a manner. The motion of the electron gets aligned. Motion of the electron or electrons, so as to say, motion of the electrons is aligned, and aligned in the same way, resulting in a net magnetic property or net magnetism, resulting in net magnetism. So this is the way the magnetism works as per the modern view, where the spin of the electron as well as the orbiting motion of the electron about the nucleus results in the magnetic behavior of the material. Now, also in case of an electron moving around the atom, well, moving around the nucleus, sorry. So this is the nucleus, and the electron moves about the nucleus in a circular orbit, of course. And in this circular orbit, as I said, that this has a certain current associated with it. Why? Because the electron is a charged particle which is moving periodically about the nucleus. Now this magnetic dipole moment that we have over here is simply I multiplied with A being the area of this entire loop, the orbit. This complete thing, the loop that it makes, is the area of that loop. And the current that is flowing over here is simply equal to the charge divided by the charge of the electron. The charge of the electron, let us say, that is E, and that divided by the time taken. Now the time taken, this is the time period of the revolution of the electron about the nucleus. So E divided by T, and as you know, it is something like T is equal to 2 pi divided by the angular frequency. E divided by T. T is simply 2 pi divided by the angular frequency or the angular speed, so as to say, that is equal to E omega divided by 2 pi. Let me just write this for you in case you have not got the hold of it. This is omega, that is the angular speed or the angular frequency, which is equal to 2 pi divided by T, and so T is equal to simply 2 pi divided by omega that I have used over here. And as we get to this, omega is equal to the area obviously is pi r squared, r being the radius in this case. So this is pi r squared, and omega is equal to V is equal to r omega. So omega is equal to v, that is the speed, divided by r. The speed being the tangential uh, speed that it has as it moves along its orbit. Now, with all these things available to us, we can just substitute the value in for m. So m, that is the magnetic dipole moment, is equal to for I, what we can do is we can use E times of omega divided by 2 pi, and in case of A, we can just use pi r squared. So the pi's can get cancelled out. We have E divided by 2 omega. We can take one of the r and keep the other one outside. Omega times of r is simply v in scalar form. So E divided by 2 is equal to E divided by 2 multiplied with V into R. So this is the magnetic dipole expression for magnetic dipole moment. Also, we know that the angular momentum, as per Bohr's postulates, the angular momentum is equal to the mass of the electron me into V into R, and this is equal to, this is quantized, so this is nh divided by 2 pi, h being the Planck's constant. And so from that, what we have, the value for Vr is that nh divided by 2 pi times of mass of the electron. We can just substitute this value over here, and we get the magnetic dipole moment in this case to be equal to E by 2, and for that Vr we have nh divided by 2 pi me. Remember, me is the mass of the electron, and m here is the magnetic dipole moment, and from that what we get is a value which is, we can keep the n outside. We have E h divided by 4 pi me. Now, putting that n aside, what we have is that this is the magnetic dipole moment for the nth orbit. So this is for the nth orbit, when the electron lies in the nth orbit, and for n equals to 1, we have the value for the uh, minimum least magnetic dipole moment. We have the least magnetic dipole moment, and that is what we term as the Bohr magneton, because it's obtained obviously from by using Bohr's quantization principle. So we have this, and we denote it by mu subscripted with b. So this is mu b, which is equal to eh divided by 4 pi times of me, and we have the magnetic dipole moment to be equal to n times of mu b. So this is the relation between the magnetic dipole moment and Bohr magneton. Now the value of Bohr magneton is fixed because all the parameters over there, they are fixed. So this value equates to nearly 9.27 times of 10 raised to the power minus 24, if I'm right, probably. And this is in, obviously, the dipole moment, magnetic dipole moment is in ampere meter squared, and this is the same as well, or it can be in per joule per second. Okay, uh, sorry, joule, not joule per second, or joule per Tesla actually, because Tesla is the magnetic field intensity. So the Bohr magneton is actually the minimum dipole moment associated with an atom due to the orbital motion of the electron in the first orbit of the atom, and the net magnetic dipole moment of the atom is few times is of the order of few times the Bohr magneton. That is how we relate it. I'm afraid we have to stop it over here. We'll keep it till here because if I proceed towards the classification of the magnetic materials right in this video, it will be a quite long one and become boring for you to sit at a stretch. So we'll be doing the classification of the types of magnetic materials based on the terms that, or based on the ideas or concepts that we have, the modern views that we have discussed in this video. And we'll be ending the series of magnetism and matter probably in the next video, which will involve the classification of the magnetic materials into dia, para and ferro, and thereafter we'll be discussing about the earth's magnetism as well. So we're looking forward to it. Till next time, thank you for watching.